How would the graph of a vehicle traveling at a constant velocity of 20 meters per second look? Assume it's traveling at a constant velocity of 20 meters per second. It would look like this: a straight flat line parallel to the x-axis. Constant velocity of 20 meters per second throughout. What I want you to try now is to chart a graph of a car which, from the moment it was at a velocity of 5 meters per second and accelerates at 5 meters per second squared, starts at 5 meters per second and accelerates at 5 meters per second squared. Okay, good. So this is what you should now see in your notebook. The first time we saw the vehicle, it was traveling at a velocity of 5 meters per second. So at x equal to 0, we mark point on the y-axis as 5 meters per second. Now, because the vehicle accelerates at 5 meters per second squared, the next second it would be at 10 meters per second, then 15 meters per second, and then 20, 25, and so on. Join the dots and we see a line. What does that line imply? It implies constant acceleration. Constant at 5 meters per second every second, or you can say 5 meters per second squared. Was the acceleration constant in the previous case? How can we explain the straight line in the previous case? Think about it. The acceleration was 0. It was 0 constantly. So what we had in the previous graph was constantly 0 acceleration, which is also constant acceleration. And in the second case, it is a constant acceleration of 5 meters per second squared. So in the velocity time graph, if we see a straight line, it's constant acceleration. Is the slope of this line positive or negative? Slope is rise over run, change in y-axis over change in x-axis. It's positive. The positive slope that we see here implies acceleration. If you are a bit rusty, have a look at our tutorials on graphs. It will help you for sure. Now visualize this. The first graph shows a vehicle with 0 acceleration. The line has a 0 slope. The second graph, the vehicle has acceleration at 5 meters per second squared, and we see this positive slope. Now try to visualize a vehicle which has a constant acceleration of 10 meters per second squared. What do you reckon will happen to this line? It'll look like this. It just becomes steeper. The acceleration is still constant though, but the slope increased. This is the line for 0 acceleration. This is for 5 meters per second squared, and for an acceleration of 10 meters per second squared, the line will only get steeper. As the acceleration increases, the lines get steeper. Can we measure acceleration in these cases? Let's start with the second chart. We see it on a new page. So we mark points A and B anywhere on the line. Say we mark point A here and point B here. Let the initial velocity of point A be u. Now let's draw two perpendicular lines from the endpoint B to both the velocity and time axis. These lines will be BC and BE. Here we have the final velocity v, and let's call this time t. Now let's discuss the different parameters in terms of the lengths here. This change in velocity is over the time period t, which is OC. And OA is the initial velocity. It's 5 meters per second. Now can you tell me which line represents the final velocity? The final velocity is BC or even OE. Both the lengths will be the same as these two lines are parallel to each other. I know it's getting a bit mathematical, but the point here is to prove the first equation of motion we've seen. Just one last piece of construction where we draw a perpendicular line from A towards BC and call this point D. Yes, we are ready. Now in this figure, can you tell me which length is change in velocity in this time interval? You're right. BD here is the change in velocity in time t. Let us make sure you understand this well. In 5 seconds, the velocity has changed by this amount. Final velocity minus the initial velocity will give us this length. BD equals BC minus CD. CD is also equal to OA, so BD will equal BC minus OA. Let's replace BC with final velocity V and OA with the initial velocity U. What we now have is BD is equal to V minus U. Let's call this equation 1. Now what is acceleration? It is change in velocity over given time. So that gives us another equation. A equals change in velocity over time taken. Change in velocity, as we know, is BD, and the period of time is OC. We get the equation A equals BD over OC. Now we have A equals BD over T, which can be written as AT equals BD. We call this equation 2. Let's look at equation 1 and equation 2. We can replace BD with V minus U. We get V minus U equals AT. We finally arrive at V is equal to U plus AT. This is the first equation of motion we'd seen in the previous video. What I would like you to try is to see if the formula works for the first case, where acceleration was 0 and velocity was constant.